So today we're going to be looking at forces. What are forces? Forces are a push or a pull. We are going to measure them in newtons as a unit. A force can change the shape, size, direction, and speed of an object. If we have more than one force acting on a body, we would then have to calculate the resultant force. A vector is a physical quantity that has both magnitude and direction, whereas a scalar is a physical quantity that only has a magnitude. So if we want to think about a vector, examples of a vector, we have acceleration, we have velocity, we have force that we're talking about right now. For scalar quantities, we have speed, we have time, and we also have mass. They have no direction whatsoever. Now, when we use vector quantities, we normally like to present the vector quantities using an arrow. Now, this arrow needs to make sense in terms of that the scaling needs to make sense, right? So, for example, if you have an arrow, let's say that you have a force of 10 newtons facing the right, and you were asked to draw a 5 newtons facing the left. They are expecting that your error needs to be within 5 or half of the one that you have drawn. So the drawing needs to make sense even though it's not up to scale, because it's especially very tough sort of scale problem, but it needs to make sense when you're looking at it to see which force is bigger and which force is small. Right? So when it comes to calculating the resultant force, we are going to choose, whenever we are given forces, we need to be able to choose which side is positive, which side is negative, so we know if we're adding or if we are subtracting. So we are with, I want you to imagine it as a contagion plate where you have your y-axis and you have your x-axis, and you know for a contagion plane it is the side is always positive. You can always choose to do that. If you make it negative, no one is going to blame you. And going up is always positive, whereas going down is always negative. This is just an example. You don't have to choose what is way. So this is to say that if your force is then going towards your right, when you are calculating, you would make it a positive integer. If your force is going towards your left, implying that this point over here is your body, the body that's experiencing the force. And if the force is going to the left, then we would have a negative force. If the force was going to the right, then we have up, we have a positive force. And if the force was then going down, then we have a negative force. So at times, our forces, when they come together, they can be in equilibrium with one another, right? So when the forces are in equilibrium, then the object will be stationary, right?
Yes.
If forces are in equilibrium, then our resultant force is going to be equal to 0. So let's look at this example here. It says 2 boys push the box from the same side with a force of 100 newtons and 200 newtons. So you can see here that we take into consideration scaling. You can see how the 200 newtons is greater than the 100 newtons. With what force must a third boy push in order to keep the box in equilibrium? So if we look at it, we're going to choose to go to the right as being positive, and we're going to choose going to right as being negative. So if we then sum up these two forces. So we want to look at the forces that we have now. We have two of them in the same direction, so we're going to sum them up and we're going to make this 300, which is positive. So in order for us to have a resultant force, so our resultant force would be a sum of force 1, let's call that force 1, and plus force 2, let's call that 1 force 2, and force 3 over there, we'll call that 1 force 3. So our resultant force, we want that to be equal to 0. So we're going to go ahead and make it 0, F1, F2, plus F3. If we substitute in the values of F1 and F2, we will get 100 plus 200, and it would get us to that point where we said we would have then 300 plus F3. Now we're going to move the 300 to the left-hand side, so it would say that F3 is minus 300 newtons. What we need to understand is that the negative at this point is indicating the direction, and the 300 here is indicating the magnitude of our force. So it's telling us that the boy needs to push with a force of 300, and because it's left and we chose the left as being negative, it should be 300 to the so far, the forces that we've spoken about have been straight line going to the left, going to the right, going up, or going down. Sometimes that is not the case. Sometimes our forces are going in an angle. And we're going to use Pythagoras' theorem for us to be able to calculate what would be our component in the x direction. For now, we call it the x direction, and our component in the y direction by just using normal trigonometry. Therefore, the y would be r, meaning the value of r, our hypotenuse, sine, and multiplied, sine of our angle, and then our x here is going to be r, and cos of r. I just want to say that whether you use cos or sine is purely dependent on the graph or on what angle they give you. So for example, let's just say that you are given this force over here. We have said this is our y direction, that is our x direction, but they chose to give you this angle alpha instead of giving you this one, because we're so used to using that angle, to call that angle beta. So if they had given you alpha instead of beta, then we now need to understand if you're using your trigonometrical ratios correctly, your x is now the opposite, and the y is now adjacent to your angle. So the x is going to become, let's call that r again, it's going to become r because it's opposite, it's going to be a sine of alpha, and our y here is going to be r cos of alpha because it is now adjacent instead of being opposite. So the angle is very much determined by the trig ratio that you use is very much determined by where the angle is. It is always important to take note of the angle that you are. So in this example, it says a flower pot of mass 8 kilograms is attached by the cables to a wall as shown. Draw a free body diagram to show the forces acting on the pot. Now, when we draw the free body diagram, it's just going to be a dot for us at that point. I want us to consider having some sort of Cartesian place so that we can have a reference. So we have a Cartesian plane, we're going to call that the y, and we're going to call that the x. Now, our 60 newtons going to the right is on our x-axis. the 60 meter is going to the right in that direction. And we have also the force X. It must go in this direction. And you will note that they gave us that angle. Now, what if you want to understand that angle out at the top? You would just draw a parallel line to that part, and you will see that this is an alternative angle. So it would then imply that that angle over there is also theta. And the last thing that we have is weight, right? Our weight going down this way. Okay. 3.2 wants us to calculate the weight. So 3.2, the weight is given by the mass multiplied by the gravitational acceleration. Our mass is 8. Our gravitational acceleration is 1.891.
And Sinelo?
Hi, guys. Okay. So 3.2 says calculate the weight of the pot. The weight is given by the mass multiplied by the gravitational acceleration. Our mass is 8 kilograms and our gravitational acceleration is 9.81. Let's put that in our calculator. We get a total mass of 78. Weight of 78.48 newtons, and the that it is going down. Question 3.2 says, what is the vertical component of the tension in cable X? So the cable X over here has two components. Cable X will have a component in the y direction, and cable X will have a component in the x direction. When cable X, sorry, y component, x component. When they are talking about the vertical component here, they want the one that is going up here. So what we can say is that this part here is stationary. It implies that our forces are in equilibrium, implying if we were to sum up the resultant forces in the y direction, then they should give us 0 because the part is not moving. Now, our resultant, right, is going to be made up of the vertical component of x along with the weight, right? And all of this is supposed to be equal to 0. Okay? So the weight has a value since we said it's going down, and we're going to choose going down as negative. It means that the value here would have minus 78.48. And therefore, our x, or our vertical component, will be 78.48. It's a positive value, telling us that the component is going up, and it has then a magnitude of 78.48. Then question 3.4 wants us to calculate the horizontal, right? So if we look at our free body diagram, we will note that the horizontal, that if we wanted to find the resultant force in the x direction, it would be equal to 0. Reason being is that our plant is not moving, it's stationary, so the sum of all the forces must be equal to 0. So we're going to choose going to the right as positive and going to the left then as negative. So the resultant force in our x direction would be the sum of the x component of our x and also the y cable. Now, because the y cable is going to the right, it would be a positive 60. And if we go to the other side, we will get the x component of our x cable is 60 newtons.
Yes.
So the next one says 3.5, calculate the magnitude of the tension in cable X and the angle which is suspended from the ceiling. Okay, so let's just draw another free body diagram that we're going to be working in here. We have our y component and we have our x component, and we understand that we have an x cable and we must go in that direction, and that's what it contains. So what we can do is we can use Pythagoras theorem, right? Because we're going to be able to create, if we move this vector, we're not moving the direction, we're just moving where it is. If we move this vector over here, it's going to create a closed triangle, a right triangle like that. So we can just use Pythagoras theorem. Pythagoras theorem tells us that x squared is equals to the x component squared and the y component squared. So therefore x will be equals to 78.48 squared plus 60 squared. And then we can put that into our calculator and see 78.48 squared plus 60 squared gives us an overall value of 98.8 newtons. Now to find beta, we can just use 10 because this is a right angle triangle. We can use our trig ratios that tells us that 10 of beta should be equals to our opposite, which is xy, over our adjacent, which is xx. So then beta would be the inverse of our xy, which is 78.48, over our horizontal component, which is 60. And we can put that in the calculator. 78.8 over 78.48 divided by 60. And that gives us an angle of 52.6 degrees, right? But this is 52.6 degrees with the left, with the negative x-axis. Sometimes they can ask you to report this as a bearing instead of just this angle. So as a bearing, all you have to do is understand that each quarter here is worth 90. So that's 90, that's 90, that's 90. You just have to add 3 90s. There's value over here. And we will get a bearing of 322.6 degrees. Questions? These are the guidance that we have coming to drawing our free body diagram. So a free body diagram is used to represent forces that are acting on the body. The body is usually drawn as just a point or dot, as you can see here. The forces are drawn as arrows in the direction of the forces. So it's very important to take which directions the forces are going to. You can see here they're pushing to the left, going right, left, going up and down. And you can see that these two are also equal. You can see by the fact that we draw these lines here, they're trying to target that. So forces will always act away from the body. It's very rare. You can draw it this way, that force there, you can draw it that way, but better to just show the arrow going from the body, away from the body, right? The arrows must touch the circle representing the object. As you can see, we draw all our arrows from this point over here. Point 2, it says the relative length of the arrow should be accurate, meaning when you're looking at those two, right, when we talk about that 78 in comparison to the 60, those two values are not far apart from each other. It implies that that line shouldn't be too big in comparison to this one over there, but it must show that you understand that the size of one force is not equivalent to the other force. If a body is accelerating, then the length of the arrow in the direction of motion must be greater than but we're going to look at this more when we do Newton's second law. It must be greater than all the other forces to show where your resultant force is going towards, which will show where the acceleration is also going towards. Number two, if a body is moving at a constant velocity, if a body is moving at a constant velocity, it tells us that we do not have any resultant force. So it implies that now the forces, in terms of their size, they must be equivalent to each other. All bodies will experience gravitational force. Anything that has mass and occupies space will always have gravitational force. So whenever you're drawing your free body diagram, start with the gravitational force. All bodies on a surface experience a normal force perpendicular to the surface. So if an object is lying on a surface, only if it's lying on the surface. We did an example with a plant. The plant was being held up, it had no normal force. So if it lies on a surface, then the surface will push back and we will get that normal force. All free body diagrams must have a key. The key is just to indicate, oh, this is the gravitational force, this is the frictional force, this is the tension, and all of that. Right. So here we have a list of forces that you are likely going to find whenever you have to draw a free body diagram. The first one is our weight. So anything that has mass and occupies space will have weight. So basically all your diagrams must have weight, all of them. We did say that weight is equals to F equals to M multiplied by G, where M is the mass and G is the acceleration due to gravity and has a value of 9.8. Just check your formulation. Sometimes they say 9.81. But we will have the perpendicular force, which will only exist, or normal force, which will only exist if we are on the surface. If we are not on the surface, it will not exist. We will have frictional force depending. Sometimes we won't have frictional force. If they say frictional force is negligible, or if they tell us that the surface is smooth, then we can assume that there is no frictional force. Also very important to note that we have two types of frictional force. We have static frictional force. This is now where no object is moving. And we also have dynamic. This is where there is movement if something object is moving. We will have a pulling force called tension, and we will have a pushing force called compression. Now, when it comes to the type of examples we've been working with, you can either work on a surface or you can work on an inclined plane. Now, when it comes to the inclined plane, you have to be able to understand that your gravitational force is going to have components, and the rest might not have components. It just depends on the question that is asked. Here, it says the stationary crate in the adjacent diagram has a mass of 100 kilograms. The angle of inclination is 30 degrees. First, calculate the frictional force between the spoon and the crate. For us to be able to do that, we need to draw our free body diagram. Now, this line, the first line that I'm going to draw, they don't actually want it, so you can draw it in pencil. Okay, don't draw it in actual pen. Then we're going to draw our box over there. We're going to have weight going directly down. We're going to have the normal force perpendicular, it must be perpendicular to the surface, so it's straight up. We're going to also have our frictional force. Now, to choose the direction of the frictional force, I'm just going to dot out our components for the weight. So you can see that the component of the weight is actually pulling the crate down. So that means friction will go in the opposite direction. Reason being is that it's there to oppose motion. So we have friction, we have the normal, and we have the weight. We can clearly see from the diagram, I'm going to make this our y-axis, and then we're going to make that our x-axis. If we look in the x-axis direction, we should say that the resultant force in the x direction, or the sum of the resultant force in the x direction, the must be equal to 0. Reason being is that they told us that this is stationary, so our resultant force must be equal to 0. So the resultant force is a sum of our friction and our gravitational force in the x direction. So how do we then calculate the component in the x direction? If that angle over here is going to be the angle that exists here between the adjacent side, or W perpendicular, what we call in the y direction, and if you were to move this one over here, it would create a nice close triangle, where that is your horizontal component. So your G is W, and that's your Y. So you will see that the WX is actually opposite of that angle. So because it's opposite, it implies that we are going to be using a sine. So we are saying all of this must be equal to 0 because it's stationary, and that would then imply that the weight, the force, the frictional force which we're looking for, is negative of our weight component in the x direction. Let's just rewrite that again. Our frictional force is equal to negative of our weight in the x direction. So the resultant weight would just be m multiplied by g. So therefore, it would be m multiplied by g sine, because it's opposite of our angle, that's theta. Our mass is 100, g is 9.8, and we have sine of 30 here. So substitute that into the equation. 100 multiplied by 8 multiplied by sine of 30 will give us 490. But it's going to give us a negative 490. Reason being is that it's going in the opposite direction that we chose as positive. Question?
No.
Then we have to calculate the normal force. We'll see that the normal force is in the same direction as our vertical component of the weight. And the vertical component of a weight is perpendicular with regards to our angle. So then we can use cos. We will then say that the sum of all of the resulting force in the y direction must give us 0 because the crate is not moving, it's stationary. And the sum of this would be the normal plus our weight in the y direction. So therefore, the normal would be equal to negative our weight in the y direction. Now, here we're going to say going down is negative, so it implies that the value of our weight in the y direction was negative to begin with, right? So we have our negative there. We will multiply it with the mass, the gravitational acceleration. We use cos of 30. So and that would give us 848.7 newtons. And because it is positive, we will say it's going up because we've chosen going up as positive. So here we have a list of forces that you are likely going to find whenever you have to draw a free body diagram. The first one is our weight. So anything that has mass and occupies space will have weight. So basically all your diagrams must have weight, all of them. They say that weight is equals to F equals to M multiplied by G, where M is the mass and G is the acceleration due to gravity, and has a value of 9.8. Just check your formulation. Sometimes they say 9.81. But we will have the perpendicular force, which will only exist, or normal force, which will only exist if we are on the surface. If we are not on the surface, it will not exist. We will have frictional force depending. Sometimes we won't have frictional force. If they say frictional force is negligible, or if they tell us that the surface is smooth, then we can assume that there is no frictional force. Also very important to note that we have two types of frictional force. We have static frictional force. This is now where no object is moving. And we also have dynamic. So Newton's first law says an object continues in a state of rest or uniform, implying it's going to be moving constant velocity unless a resultant force acts upon it. And we call this property here the law of inertia. So as explanation, inertia is the property of an object that causes it to resist a change in its state or uniform motion if it's a uniform motion or at rest. So let's look at a practical example. It says when a car stops suddenly, a person resting on the seat slides forward. Now, understand that the car was moving forward at the beginning of the journey, right? And so when you then stop the car, the box or the parcel still wants to move in the same direction. And that is why it will continue to go forward, and it would look like it's sliding off the seat. Sometimes it does slide off the seat, depending on how hard you hit the right. Then we look at the second law. Before we look at the second law, we have to define some things. It says that the mass is the amount of matter a body is made up of. And in terms of acceleration, it is the change of state of motion of a body, or we can see it as a change in the velocity over a change in time, or we can see it as the rate of change in velocity. So Newton's second law says if a body is in motion, then the resultant force is not zero. The resultant force would be given by this equation over here. And if we were to rewrite the equation, we would have it as F net over M. So what that is telling us is that the acceleration is directly proportional to the resultant force. This tells us that when the resultant force increases, so will the acceleration. If the resultant force decreases, so will the acceleration. It tells us, secondly, that acceleration is inversely proportional to the mass. So this implies that if we increase the mass, then the acceleration will decrease. And if we decrease the mass, then the acceleration will then increase. So if we were ever asked to write down the definition of Newton's second law, let's say an inert force F is applied to an object of mass m, it accelerates in the direction of the mass force. That the acceleration is directly proportional, right? Meaning when one increases, the other one will increase. One decrease, the other one will decrease, and inversely proportional to the mass. Meaning if the mass was to increase, the acceleration would decrease. If your mass was to decrease, then the acceleration would increase. Then this is the actual definition that you would have to write down. So Newton's first law says an object continues in a state of rest or uniform, implying it's going to be moving constant velocity unless a resultant force acts upon it. And we call this property here the law of inertia. So we have Newton's third law that says when object A exerts a force on object A, object B simultaneously exerts an oppositely directed force of equal magnitude on object A. So this law involves pairs of forces. There needs to be an action and a reaction, like a weight and a normal, which always act on different objects and therefore they do not balance each other. So it should make sense. It should be a, okay? Makes sense?